AP Physics. Doing 41 to 47 odd from chapter 15, Simple Harmonic Motion. In number 41, we've got a physical pendulum. It looks like something like this. Axis is here. And so you've got a uniform disk here with a radius of 0.10 meters and a mass of 0.5 kilogram, attached to a uniform rod with a length of 500 millimeters, which is 0.5 meter, and a mass of 0.27 kilograms. And we want to calculate the rotational inertia of the pendulum about the pivot. So let's see. The total rotational inertia is equal to the rotational inertia of the rod plus the rotational inertia of the disk. I think it's important to write that out. In a free response question, it's likely there's a point attached to recognizing this. So the rotational inertia of the rod about its end, if you remember, that's 1/3 mL squared plus the rotational inertia of the disk. There's two different ways we could do this. Maybe I'll just quickly do it both ways. You could treat the disk like an actual disk, which would be in 1/2 mR squared plus the parallel axis shift would be the mass of the disk times the shift. Now, we're always shifting from its center of mass. So the center of mass is the center of the disk, and it's now not rotating about its center of mass. It's been shifted all the way this far from the axis. So that's 0.5 plus another 0.1. So that's 0.6 squared. And we run that calculation here. I'll do them separately. 1/3 times 0.27 times 0.5 squared, 0.0225. I'm doing them separately because I think it's probably a good idea to see what they are separately so we can see how much they contribute. I'm also going to do this separately. That's 1/2 mR squared. So just noticing so far, that's about 10% of that. So it's a fairly small contribution compared to that. Kilogram meter squared, that's units for a rotational inertia. And then here, 0.5 times 0.6 squared, 0.18. And, well, maybe I won't run both, well, we'll try it both ways. But here you can see that this, the disk on the end, that mass, it's more mass than the rod, and it's also further away from the axis. So in the overall rotational inertia, the mR squared scheme, this is contributing a whole heck of a lot more than anything else. This is contributing about, maybe 7 times as much as this, and this is then only 10% of that. So when I add those up, I've got 0.0225 plus 0.0025 plus 0.18. I get a total rotational inertia of 0.205 kilogram meters squared. if you treat the disk as a particle, because it's kind of far away from the axis, so just instead of treating the disk like it's a 1/2 mr squared disk, to say, you know what, the disk is kind of far away from the axis, so kind of like the kid who's jumping onto the edge of the merry-go-round, I'm just going to treat it like a particle. The difference would be that we would not consider this term. We would take the whole thing as if it was an mr squared, where the r was this far away. So it's the same as the mr squared is the same as the parallel axis shift. If we did that, we get 0.18 plus that. And you can see what the difference is between those two. It's pretty dang small. And if you want to know as a percent, oops, I messed that up. Hold on a wee second. So 0.205 so it's about a 1% difference in the rotational inertia there. So you could probably go either way. I'm going to go ahead and use this in the calculation. You can try it with both, but it's going to make a small difference in the answer. Okay, so that's part A. Part B, we want to know what's the distance between the pivot point and the center of mass of the pendulum. Okay, so we have to do a center of mass calculation here because we need to know that. So I've got the rod and then I've got the disc here, and I want to know what the center of mass is. I'm going to take this to be y equals 0 right here, and I know that the y center of mass is equal to 1 over the mass total times m1 y1 plus m2 y2. I'm taking this to be the 0 coordinate because then the actual distance I get, that will be the center of mass. It'll be that distance that I'm interested in. So the total mass is 0.77 kilograms. And then for y1, I'll take that to be the rod. The mass of the rod is 0.27. And the center of mass of the rod is right in the center of the rod. Since the rod's 0.5 meters long, that's 0.25 meters. Right? So that's kilograms, that's meters. And then the disc has a mass of 0.5, and the center of mass of the disc is at 0.6 kilograms. So that's not a complicated thing to do. Just have to do it. So let's see, I've got 0.27 times 0.25 plus 0.5 times 0.6 all over 0.77. Hopefully we should get something that makes sense before I hit enter. I'm expecting something kind of somewhere in this range, probably 0.3 to 0.4, something like that. Oop, maybe a little bit more than I thought, so 0.477. And actually, in retrospect, that makes sense because the disk has more mass, so the disk is more influential here. It's pulling the center of mass further down here. So it's almost at the end of the rod there. Okay? And that's the answer for part B. And now I'm ready to do part C, where I calculate the period of oscillation. So we've derived this now. I'm not going to go through that. The period of a physical pendulum is equal to 2 pi times the square root of I over mgd, where d is the axis to center of mass distance. So that's 2 pi times the square root of I over m, the mass of the whole thing, is 0.77 g, and d, the distance between the axis and the center of mass. That's what I found here. So let's find that. It's 2 pi times the square root of 0.205 over 0.77 times 9.8 times 0.477 is 1.5 seconds. And I'm just going to flip to the back of the book here and check my answers real quick. Make sure that I'm not leading you astray. So it looks like we are 41.5. So they did the 0.205. They did it the same way that I did the first way, 47.7 centimeters in 1.5 seconds. So we're good. That's it. All right, number 43. If the physical pendulum in figure 1511, so if you haven't, you need to flip back in the book and find that example in the chapter. But the example, if you process what's going on there, and if you didn't, you can watch what I'm doing here and then just redo this problem. They had a physical pendulum of length. I think they just called it of length L, didn't they? Or did they give an answer? I don't think they did. Oh, it's a meter stick. So the length is equal to 1 meter. And in the problem, they found the center of mass here, and they found the point P, which is sometimes called the center of oscillation. We're not going to talk about that a whole lot, but in the problem they explained that that's the part where if you hung a simple pendulum next to it, where all the mass was concentrated at the end, those would swing with the same period. We call it the center of oscillation. So they said, what if you inverted this and you suspended it from point P? And if you read through that problem, you don't have to redo this, you just have to process what's going on in the problem, that this distance here to point P is 2/3 L. So now they want to take this thing and put the axis at point P. Of course, the center of mass is still in the center. So this is 2/3 L, which means you need to do a little bit of math here. So that's 1/3, this is 1/2. So pause the video here for a second. You need to figure out what fraction of the meter stick is this. It looks like it's a quarter the way I drew it, but it's not. And the distance from the axis to the center of mass, that's equal to, that's what we call D. That would be L over 6. That's 1/6 of the distance. So it's just a little fraction math there to get that. Okay, so they want to know what's the period of oscillation now. So the period of this physical pendulum is equal to 2 pi times the square root of, what's the rotational inertia of this? Well, let's see. Rotational inertia of a rod about the center of mass is 1/12 ml squared. That's about the center of mass. I don't put that there. Sorry. I'm going to leave that out because I'm going to do the parallel axis. And then the axis shift, we have, that's m times the shift squared. So how much have I shifted from the axis? Well, it's the same as the d, right? It's the axis to the center of mass. So that's L over 6 squared. So 1/12 plus 1 over 36 is 4 over 36, which is ml squared over 9, I think, when we simplify that, right? This is going to be over 1/36 of an ml squared, and this is 1/12, so multiplying by 3 would be 4 over 36. Yeah, that's right. So here we've got I over m g, and then the d is L over 6. So the m's cancel out, one of the l's cancels out, and then I have a 9 on the bottom and a 6 on the bottom of the bottom, which flips to the top, so that's 2/3, and then one L on the top and a G on the bottom. And they want to know, is the period now greater than, less than, or equal to its previous value? And if you look back in the problem, that's actually equal to its previous value. And let's check our answers. I'm just comparing that to the answer that they already did for us in that example problem. Sorry, get these papers out of the way. And they actually got an answer for this, so maybe they actually gave, oh, I guess we knew that. We know the L, right? So you can plug that, it's 1 meter long, so you can plug that in, and they get 1.64 seconds for that. Number 45. A performer seated on a trapeze is swinging back and forth with a period of 8.85 seconds. She stands up, raising the center of mass of the trapeze and performer system by 35 centimeters. So difference between here and here would be 0.35 meters. Then what would be the new period of the system? So we're treating this like a simple pendulum, like all the mass is right there at the end. So the period of a simple pendulum is 2 pi times the square root of L over G. So for the original, or let's say that's the initial period, if you want, before we changed things, then we could say, we know what that's what, 8.85 seconds. So 8.85 is equal to 2 pi times the square root of L over 9.8. And notice the only thing we don't know here, it didn't seem like you had a lot of information, but the only thing we don't know is L. So L is going to be equal to, if we square both sides, my 8.85 will still be up here. I need to divide by 4 pi squared here, and then 9.8 will be up here. And check my math there. I think that's right. So I'll check that. So that means the length is 8.85 times 9.8 divided by 4 pi squared. So about 2.1, well, let's say 2.20. They're doing to the nearest centimeter, so I'll follow suit there. And then, so that means our new length here is 35 centimeters shorter than this. So that's going to be 1.85 meters, right? This less 35 centimeters. So the new period is going to be 2 pi times the square root of 1.85 over 9.8. Oh, that's So the new period is now 2 point. That doesn't make any sense because the old period was 8.85 seconds. It would not change it that much. So that did I do wrong? Let's see. Squared both sides. Oh, did I not? I didn't square this. Let's go back there. Sorry about that. That's why it's a good idea to look at your answers and make sure that they make sense. So this trapeze is much longer than we thought. It's 19.4. Can you see that? 19.44 meters. So that means when I subtract 35 centimeters, I have 19.09 meters. So this is 19.09 meters. So let's try that again with 19.09. That makes a whole lot more sense. 8.77 seconds. So the old period was 8.85, now it's going to be 8.77 seconds. Just check that real quick. Yep. And last one from this set. Here's a classic physical pendulum problem. We've got a uniform disk, there's a center of mass, and we've got an axis here. The radius of this thing is 0.0235 meters, and a pivot is located 1.75 meters from the center of the disk. So that's my axis to center of mass is 0.015 meters. And that's my D, right? Axis to center of mass. And we don't know the mass. Oh no, does it matter? Well, hopefully it will cancel out. So the period of a physical pendulum is 2 pi times the square root of I over mgd. So let's see, 2 pi times the square root of the rotational inertia of a disk is 1/2 m times r squared over m g d. And sure enough, the masses cancel out. So we've got 2 pi times the square root of 1/2 times 0.0235 squared over the quantity g times 0.0175. So it's going to have a period of about 0.25 seconds. Just give that a quick checky in the back of the book. And that is not correct. So now we go back and see what we did wrong. Let's see. Did I make some kind of big mistake, or did I just put a number in wrong? Let's see. Uniform solid disk. Oh, I know what I did. Do you know what I did? If you don't, maybe you already do. I bet you already do, because you're clever. Pause for a second. I know what I did. I used the rotational inertia of the disk about the center of mass, but of course that's not the axis. So I forgot the parallel axis theorem. So the rotational inertia of the disk, it's the I, the center of mass, plus the parallel axis shift. So I forgot to do that. So this is m r squared plus mh squared. So that's 1/2 mr squared. That's for a disk about the center of mass. So let's see, that's 1/2 mass of the disk I don't know, that's an m, times the r squared. So that part's the same. M r squared plus m, and then it's shifted 0.0175. Right, the shift and the d are always going to be the same thing. You think about that. That makes sense. So I'm going to figure out the coefficient of this m here. So let's get rid of this. So it's 2 pi times the square root of 1/2 times 0.0235 squared plus 0.0175 squared. I'm just doing this as the coefficient of the m. So that is m times 5.82 times 10 to the negative 4th over m g d. So the m's cancel out, and we get 2 pi times the square root of 5.82 times 10 to the negative 4th over the quantity 9.8 times 0.0175. That should do it. And that gives me a period of 0.37 seconds. And I think that agrees with, yeah, or 0.0366 they have. Check.